Okay guys, let's take a look at our lesson for today. What we're going to be looking at today is working with limits algebraically. The other day, just the lesson right before this, we looked at numeric and graphical limits, which were great. So we're just going to go on to the third type that we work with, basically is algebraic. So the first thing I'd like to talk about are limit laws. Okay, so limit laws are pretty important. They're kind of a formal way to split limits up. Sometimes it's quite handy for us to be able to rewrite a very complex limit into tiny little pieces. That's very helpful sometimes. And so there are actually a lot of limit laws that we can use, and these are written up here. So if I am taking the limit of the addition or subtraction of two different functions, I am allowed to break them apart. I can do the limit of the first one, and then do the limit of the second one, then add or subtract their results. So that's kind of handy sometimes if it's real complex. So if I also, the second one is if I have, say, like the number 2, a constant, some number in there. And maybe, I don't know, it's a fairly complex limit, and I want to pull that, I am allowed to pull that constant outside of the limit. And then what I would do is take the limit and then apply that constant, or multiply the constant to the result of that limit. We are allowed to break apart functions that are being multiplied. So I can say the limit as x approaches a of f times the limit as x approaches a of g, and do those separately and then multiply the results. Are we kind of getting the idea of what limit laws do? They just break it up into little pieces. If we're dividing, we are certainly allowed to split a division up as well. We, of course, have to be careful, as we always are, if the denominator is 0. We know that's not a good thing, right? Not a good thing, so can't have the denominator be 0. If our function is raised to a particular power, and it would make our work easier to, basically we are allowed to take the power outside the limit, take the limit of the function itself, and then apply the power to it. So that's an okay thing. Same thing with radicals. I am also allowed to, if I have a function that's, like the cubed root of something or the square root of something, I am allowed to take that radical to the outside of the limit, take the limit of the function, and then apply the radical. So those are just some pretty important things for us to know, that we are allowed to do those things. Okay, we're going to practice limit laws on the next page. So algebraic limits, there really are only 3 kinds of situations you're going to face. Just 3. Okay, this is the first kind of situation. The first situation, this is what we always start with. We start with the first kind of situation. We plug in a. So whatever this number is, we plug it in. Okay, that's the very first thing we do. If we get an answer, we're done. Okay, that would be if we were lucky. That kind of rarely happens, right? If we just get an answer, we're done. So, but that is certainly legitimate. We plug the a in. If we get an answer, we're done. That's the first kind. The second kind of limits we'll be dealing with is, okay, so again, we plug the a in, see what happens. We get 0 over 0. This is called an indeterminate form. Indeterminate form. And, in English, indeterminate means you can't determine, right? That's what that means. And it's kind of actually fun. When you get that, you can think, oh, yes, I have more work to do. This is fantastic. It's like a hidden treasure, right? We know there's an answer. The answer isn't 0 over 0. The answer is something. It could be 5. It could be negative 20. It could be 0, but I don't, I've seen students say 0 over 0 is 0. That's really not the norm. And we've got to really do some investigation and figure out what it is. The investigation I'm talking about is using algebra and trig to simplify. That's what we would do. Use algebra and trig to simplify. So some things that we would try, we'd try factoring, multiplying by the conjugate. Now this is kind of important for us. We are only allowed to multiply by 1. Only allowed to multiply by 1. I don't have an equation, I can't balance the equation and multiply by the same thing on both sides, so I can only multiply by 1. So if I'm going to multiply by the conjugate, I have to multiply by the conjugate over itself, is what I have to do. So that's just a note. Finding a common denominator, that's something that we might try. So these are all different algebraic things that we would try in order to deal with this indeterminate form of 0 over 0, or There are also infinity over infinity. I don't know that I have any of those in here, but those are the two basic indeterminate forms that we would deal with this year. I know, so there are other indeterminate forms. I know you're probably really excited, like, oh my gosh, are there others? Yes, there are, but we will not deal with them until next year. Okay, these are the most basic, straightforward indeterminate forms, 0 over 0 or infinity over infinity. So this is the second type. When we get, we plug the A in, we get 0 over 0, we're like, yes, we get to keep working, right? We get to try some more stuff, find our little buried treasure. This is the third kind. And there's only 3 kinds, guys, only 3 kinds. The third kind is when the denominator is 0, and this is only the denominator. Right? Because if the numerator is also 0, it puts us into the second type. Right? This is only if the denominator is 0. Like, for example, maybe 2 over 0. Maybe that's our answer. We got 2 over 0. So if that happens, that's the third different kind. So what that means 95% of the times is that there's a vertical asymptote there. That's what it means. So we get like 2 over 0 or something. What we're required to do is we're required to do both the right and the left-sided limit. Why? Well, let's think about it. So let's say I have this function. Let's say there's an asymptote at 1. Okay, well, what's happening? We need to know what's happening. We don't just ever write down D and E and move on. That's not a thing. We have to investigate. What does it mean? What's happening? Is the function approaching from the right, and going to infinity, and from the left? Is that what's happening? If that's what's happening, then we would say that the limit is tending to infinity. Right? So those are things we have to investigate. Well, how do we investigate that? What we do is we go to 1/10 on either side of A. So we go to 1/10 on either side of A. For example, in this case, I would want to investigate what happens to the function if I'm at 1.1. Am I going to get a positive or negative number? That's what I'm looking for. I'm looking for the sign, positive or negative. That's what I'm looking for. Because if I am 1/10 away, if I'm really close to this asymptote and my value is positive, that means that this is going to tend to infinity. If I'm really close on this side, 1/10 away, so in this case, if this is 1, we'd be at like 0.9. If I'm 0.9 away and I'm going to have a positive number, then it's tending to infinity. Does that make sense? If it has both, if it goes both ways. So let's say we'll just use our example. Let's say from the right it's going to infinity, from the left it's going to negative infinity. What we would say is D and E, because from the right we're headed to infinity, from the left we're headed to negative infinity. That's okay. Otherwise, if they're consistent, if we're going to, both from the right and the left we're going up, this would tend to infinity. And likewise, if they're both going down, that would tend to negative infinity. Okay, so our 3 options for number 3 is answer is either going to be infinity, negative infinity, or D and E, because it's going both ways. Does that make sense? That's all we got. Those are our only options. There aren't any other options. Okay, so hopefully that will reduce some of the confusion. Typically, students are most confused with this third type. And then I get students that try to go 1/10 on either side from anything. Okay, so this technique, going 1/10 on either side, only applies to this third type when I get some number over 0. Okay, questions so far? So I have some examples actually of all these different kinds of things on the next slide. So let's move to the next slide so we can work through some of these things. On example 1, and I should have included a use limit loss. So let me be very specific about what that means. When the instructions say use limit laws, our minimum number of limit laws to use is 1. You have to use 1. Okay? What that's doing is testing to see whether you know how to use a limit law. It would not be acceptable to just write an answer. I just want to be clear about that. So that's only when it says use limit laws do you have to use limit laws. Once I teach limit laws, sometimes students try to use limit laws for everything. Like these problems over here. The only reason that you would use a limit law in a problem like this is if it made your life easier. Okay, that's what you would do. That's when you would use a limit law in a problem like this, is if it made it easier for you. If it doesn't make it easier, then don't use them. Okay, but when it says use them, we have to do a minimum of 1. So let's work through that. This is the sum of 2 functions, and notice that we're just given some distinct points. We have no idea what the functions are. We have no idea. But we do know what the limits are as x goes to 3 and as of f and as x goes to 3 of g. We know what those limits are. So the first thing I'm going to do is I'm going to rewrite this. So the limit as x goes to 3 of f of x plus the limit as x goes to 3 of g of x. That's my required limit law. There we go. It's written. So now I'm going to use substitution, and I'm going to replace limit as x goes to 3 of f of x with a 2. And then I'm going to replace the limit as x goes to 3 of g of x with a 0 to get my final answer of 2. Okay, so that's an example using the addition limit law. Okay, let's look at the next one. So this is a division one. There are several ways that you can write the limit law. I'm going to choose to write it as like a fraction, that kind of division. So the limit as x goes to 3 of f of x over the limit as x goes to 3 of g of x. Okay, I'm just going to write them like that. So now I'm going to substitute, and in the numerator we know that that's a 2, and the denominator that's a 0. Okay, that's a problem. And by the way, we certainly is viable for us to write equals a number for a limit, but it is not okay to write equals 2 over 0 or equals infinity. That's not okay. I know it's a nuance, but we got dinged on that actually last year on the AP test. No writing equals when it's not a thing, like 2 over 0 or 0 over 0 or infinity. We don't write we don't write equals. So arrow, we do arrows. All right, so that is undefined. Typically, if we knew what the functions were, we would investigate to see which way we were going, because this is the third type, right? We're either going to positive infinity, negative infinity, or combo. But we don't have the functions. So we really don't have much choice but to say D and E, and since we said D and E, we always say a reason, because that number is undefined. And you can say, be more specific and say because the number is undefined, or you can just say because undefined. Okay, that's why that one is D and E. Now that would not be acceptable if we knew what the functions were. We wouldn't be able to say D and E because undefined. We would have to again investigate. Which way are we going? Are we going to positive infinity, negative infinity, or combo? Okay. So the last one that we are required to use limit laws for is this part C. So this is a product. We're going to split it up by multiplication. So the limit is x goes to 3 of x squared times the limit is x goes to 3 of f of x. Okay, so this is just a regular limit where we just substitute, just plug in the number. All right, plug a 3 in, I get 3 squared, which is 9. This one we're going to substitute from our information up here. It's a 2, so my answer is 18. Now the reason that I'm doing this example is because this is one of the most common types that confuse students. I can't tell you how many students have given me on this particular problem the answer of 2x squared. That was their answer. 2x squared. Right? Well, why didn't you take the limit of the x squared? You see what I'm saying? So it's real clear when you split it up like this, oh, well that's just a regular old limit, right? I just take that regular old limit and oh yeah, I substitute there. So hopefully that clears up any problems that we might have with that. Okay, are we good with limit laws? All right, so now the next ones, we're just doing those algebraically. I'm not going to use a limit law unless it would help me. Okay, so the first thing we do, we go with step 1, is we plug in the number, plug in a -1. So I put a -1 in here, and I get, what, 1, -2 times -3. I get a 0 in the numerator, and a -1 gives me a 0. So, yay, that's exciting, right? That means, oh, there's buried treasure. What's the answer going to be? I don't know. Let's look. So, what should we do? So multiplying by the conjugate on something like that, it usually doesn't help at all, so we really shouldn't really think about that. That one, let's factor. I mean, that would probably be a good technique, right? We could factor. That denominator is a difference of perfect squares, so maybe something will happen that will help us. So we're going to factor. Okay, so the bottom is x plus 1, x minus 1. Let's see, the numerator. Have x, see it's subtraction, so the signs are different. What do we have? 3 and 1. Okay, does that look good? So x minus 3, yep, that's the factoring. So when we factored, we discovered something. We can cancel out a factor, right? So this factor cancels with this one, and that leaves me with the limit as x goes to -1 of x minus 3 over x minus 1. That's what it's left me with. Okay, so now let's again, once we have rewritten it, we're going to try again. We're going to plug the number in again. Let's plug in a -1. And so I have -1 minus 3 over -1 minus 2. Notice how I'm not writing the limit anymore. I'm just going to put arrows between these. I'm not writing the limit. Why am I not writing the limit statement anymore? Because I'm taking the limit, right? I'm putting numbers in. When you put the numbers in, you don't need the limit statement anymore. In fact, you shouldn't write the limit statement anymore when you're putting numbers in. So I'm putting in numbers. So what is that? That's -4 over -3. So it looks like my answer is 4/3. Okay, we okay with that? Let's think about this graphically. So this is a rational equation. We've worked with those before, right? We've worked with rational equations before. What happens when we cross out a factor of a rational equation? What does it leave for us? Do we remember? A hole. It leaves a hole, right? So basically this is a rational, function with a hole. It's got a hole at -1. And this is the location of the hole, right? The y value of the hole. Do we remember that from our rational unit? You're like, what? Rational unit? Yes. Oh, yeah, that's a 1. Thank you. That's a 2. That's a 2. Can't even copy. There we go. Thank you. Are we good? Okay. All right, so let's go to the next one. So I'm going to substitute a 2 in. And when I do, I get -2 over 0. This is the third type. The third type, when we get some random number over 0, that means that there is an asymptote there. So what am I required to do? Well, I'm just going to write this out in 2 pieces like this. I'm going to do the limit as x goes to 2 from the right, and I'm going to do the limit as x goes to 2 from the left. I'm going to do both of those. This is where we use the technique where we go 1/10 on either side. I'm going to call this function f. Okay, just so I have a name there. Okay, so let's think this through. So 2 from the right. So I would plug in a 2.1. If I put in a 2.1 here, I get a positive number squared. Okay, I still get, that yields a negative number. So that means that's going to negative infinity on that side. So I'm coming from the left, and that would be like a 1.9. And you can do this in your head, or you can write it out. It's up to you. So I put a 1.9 in here. 1.9 minus 2, that would be negative. But that negative is squared, isn't it? So since the negative is squared, this side is still going to be negative. So it's going to negative infinity. So basically, that's our result. Our answer is negative infinity. Because that's what the answer, what we're trying to get to is what's happening there. Where is the function going? Is it going, on both sides? This means on both sides it's going down at that asymptote. Okay, are we okay with that? All good? Okay. So let's substitute a 0 in. So square root of 3 minus square root of 3 is 0. Oh, look, another prize. Yay, 0 over 0, indeterminate form. So when we look at this one, factoring's probably not a thing for that. When we have radicals that look like that, this is the classic one that's perfect for multiplying by the conjugate. Usually the multiplying by the conjugate is with radicals. It's very rarely with polynomials. I'm just telling you because some students try multiplying by the conjugate all the time. Okay, so it usually just works with radicals when they look like that. And again, I can't multiply by anything but the number 1. So I'm going to multiply this by the square root of x plus 3 plus root 3 over the square root of x plus 3 plus root 3. Root 3. Okay. So here we go. Let's do that. Limit x goes to 0. So another thing I want to caution you about is when we're multiplying, we only multiply out the conjugate parts. Do not multiply out the other part. For example, in this case, we're just going to multiply out the numerators, not the denominators. If the conjugates were in the denominator, we would just do the denominator and not the numerator. Because if you do both, then you might disguise the present that's going to be waiting for you. Right? It might be lost. It might get lost in there. And it has happened many times. Students get lost. So please just listen. Just do the conjugate part. So here we go. So the square root of x plus 3 times the square root of x plus 3 is x plus 3. Conjugates, outside, inside, when we're foiling, go away. That's, the beautiful thing about conjugates. Negative root 3 times a positive root 3 is negative 3. All over x times, resist the temptation to multiply, resist, 2 times the square root of x plus 3 plus square root of 3. Okay, so let's see what we have going on here. So I have this 3 minus 3, that's going away. And I'm left with x, so let's rewrite it. So limit x goes to 0. I'm left with x over x times square root of x plus 3 plus square root of 3. Okay, do we see what magical present happens with us here? Yes, those x's cross out, right? If I had distributed it, it would be disguised and I wouldn't be able to tell. Okay, so don't do that. All right, so these go away nicely. Now I can plug in again. So we're going to plug in 0. So in the numerator, there's still a 1 there. I'm sure we are good with that, right? There's still a 1 there. So 1 over. Notice I'm not writing the limit statement anymore. I'm done with it. I'm plugging in. 1 over. So let's see. 0, plug in a 0 here. 0 plus 3 is 3. So square root of 3 plus square root of 3. That's what I get when I sub in a 0. But I would want to clean that up a bit, right? So that would end up as 1 over 2 root 3. Okay, how's that? We good? All right, last one. Yes. No. We rationalizing in pre-cal and calculus, we just don't even do that anymore. It's important to know how to rationalize because, for example, on the AP test, some of the questions might be rationalized. The answer choices might be rationalized, but we know how to do that. We've been doing that for a long time, so we don't ever have to rationalize in here. Okay, so let's look at our next one. So I'm subbing in a negative 3. Negative 3 minus 1 is negative 4. 1 over negative 4 plus 1 over 4 is 0. Oh, look at there. Of course, right? Another fun one. So let's think about what technique that we might try. Conjugate. No, I'm not seeing conjugate there. I'm not seeing factoring. It looks like that just kind of screams to me, fix the complex fraction. I mean, that just screams that. Get a common denominator, fix the complex fraction. So that's what I'm going to do. So I'm going to add these fractions together. So I have the limit as x goes to negative 3. I'm going to add these fractions together, and I'm going to do the common denominator at the same time, all at the same time, like several steps in one. I hope we're okay with that. So our common denominator would be 4 times x minus 1. And on this fraction, I would need the 4. And on this fraction, I would need the x minus 1. And that's all over x plus 3, and I'm just going to put that over 1 to be clear where the main fraction bar is. That's the main fraction bar. Okay, so let's clean that up. So limit x goes to negative 3. So I combine like terms in the top here, so 4 minus 1 is 3, so I get 3 plus x over 4 times x minus 1 times, I'm going to fix the complex fraction, I'm going to bring that up, instead of dividing, multiply by the reciprocal, 1 over x plus 3. Okay, do we see anything? We do, don't we? Very nice. Very nice. This is going to cancel with this. So basically, I'm going to be left with 1 over 4 times, I'm going to plug in a negative 3, negative 3 minus 1. So what is that? Negative 4, so 1 over negative 16th. Okay, and those are the three main types that you'll see, like factoring, multiplying by the conjugate, and fixing complex fraction. Those are the main three types that you will see. All right, questions for me. Are we okay? Okay.